Hello. PogChamp. I don't know what that means. PogChamp. Champ is like buddy. Pog means I don't know. Okay. I have as being here. Good morning, Ellie. I have here Claire, Charlotte, Ellie, Jasmine, Saskia, Alicia, Jacob, and Konstantin. Would one of you please Fevka. Okay. Who's Fevka? Okay. Vicky's here. Could you guys, somebody put in the class chat that this is happening just in case somebody missed it? Hi, Felix. But is actually wonderful. Yeet T. Oh, is that Chris? Chris, right? That's Chris, right? Good. Okay. Chris. Okay. All righty. We're at 10:01. Hope you're all well. We're all well here. Okay. So looking for, oh, it's Richard. Thank you. All right. Oh, yeah. Chris is the Darth Vader guy, right? Okay. Looking for Ryan Gilbert, James, Carlos. Hi, Sophie. Errol. Sadie. Okay, Errol is there, but he can't write messages. Okay. All right. Sadie. Yuri. Oh, hi. Hagen. Yuri, and then Finton. Oh, hi, Finton. Okay, 1, 2, 3. I have 6, 8, 9, 11, 16. And there's 17 on here. Maybe there's somebody lurking or whatevs. It's cool. So again, Ryan, James, Carlos, Sadie, Chris, Yuri. If you are here, say hi, please, because I haven't marked you as present yet. Okay. Good. I have only 30 minutes with you, so I want to get going right away on actual work. We do have this week 2 live streams to get caught up to the other class. We meet again tomorrow from 9 to 9:30. And after that, we have spring break. Hi, Yuri. So I have for today as a topic, which I think is quite appropriate, is 2 things, namely wave speeds. We're going to talk about wave speeds. And because when we're talking about wave speeds, oftentimes about the speed of sound and the speed of light. Both those numbers are really big. And I just want to write them down for you. So the speed of sound is normally, and that means under normal pressure and temperature conditions, that's a very big number, 343 meters per second. But it's not remotely as large as the speed of light, which we also just call c, which is 3 times 10 to the 8 meters per second. And in casual conversation, sometimes we'll call this 300,000 kilometers per second. So, hi, Yuli, I got you. So wave speeds, these are very large numbers. So today's topic is wave speeds and large numbers in general. Because you guys, as any humans, so you don't have to feel bad, have a problem understanding large numbers, which is one of the reasons why politicians are so effective at getting you to pay for aircraft carriers, right? They're like, whoa, we can buy an aircraft carrier for 25 billion. And you're like, cool, let's get 3. I don't know. I don't even know how much money that is. I don't care. So in that context, it's important to orient yourself as to the number and not just say, well, that's really big. I don't know. Million, billion, trillion, those are just large numbers to most of us. In your personal life, you have a pretty good idea at this point of your life what 100 euros is. You probably have also a pretty good idea what 1,000 euros is. That's what an overpriced iPhone costs. You can maybe picture 10,000, maybe 100,000, but even after that, at 1,000,000 euros is kind of the cutoff where normal humans can still kind of get it. So 1,000,000 euros is kind of where a nice house in Berlin might be priced, 1,000,000 euros. And you can kind of picture that, oh, I got a house. Okay, but if you go beyond that to 1 billion or 1 trillion, things get absurd. And in that context, we just had an absurd number in the news. And the news number is that in the United States, the Congress just passed a coronavirus relief bill. And they released what they came up with was $2.2 trillion. That's the amount of money that the United States is putting in this bill to basically help with the economic consequences and maybe also the health impact, I hope, of the coronavirus. That's a really big number, and you have really no good idea of how to picture that. I could write it out. Americans put the dollar sign first. So, but that number is just really big. And let me illustrate that to you by saying, well, what happens if I add 3 zeros? And you're like, man, it's still really, really big. I have no idea. Hi, Ryan. So the 3 zeros obviously are not on here. That's wrong. But this is the amount. What does that even mean? And the important thing when you have these kind of numbers is that you need to somehow bring them into a human scale. So you need to make it comprehensible because $2.2 trillion is not comprehensible. Okay, just way too big. So what helps in this context is comparing it to another quantity that makes sense. Like you know how much money you have or how much money you'd like to spend on a phone, or even hopefully you have a general idea of what a family budget would be like, or if you had a normal job, not hedge fund manager or NBA basketball player, but a normal job, how much money you could make. Okay, so a few $1,000s a month, by the way, that's kind of what you're looking at, right? So good. Lil Curls. Good morning, Lil Curls. Hi, Henrik is here. Hello, Henrik. Good to see you, buddy. Okay, Lil Curls. Who's Lil Curls? Can you identify yourself? Maybe I'm supposed to know who that is. Is that Carlos? Lil Curls, Carlos? I don't know. Anyway, so let's put it in a context that makes sense. What we're going to do with that number is we're going to divide it by the population of the United States. Hi, Chris. Good. So Chris is here. Good. So is to divide by the population of the United States, which is 330 million or something like that. Okay. And if we do that, you can do that with your calculator. I'll do it with my calculator. It's actually pretty easy. Okay. We get out, it's about, that's 2/3, which is 6, 7. So I get 6,000. Whoopsie. 6,000. I'll round to this digit. $700 per American. Okay. So that is something that's comprehensible now. And you can understand what kind of money we're talking about when we say the Corona bill is valued at $6,700 per American. And that's man, woman, and child. It's not just adults, it's everybody. So that means, for example, that for a family of 4, like we're 4 blessed people, right? So for 4 people, we're looking at $27,000 dollars, $27,000, 25,000 euros, something like that. So just to give you an idea of how gigantic-enormous this is, even though you knew this number was gigantic-enormous, now you have a better idea of what it means. Because if I say it's 25,000 euros per family, that's a very realistic number that you can wrap your head around. Oh, that's the amount of money that a lot of people, if you were Kita Erzieherinnen, you might make 25,000 euros a year. Your entire salary for your year is how much a family on average is basically spending on this. Because again, the US government obviously is, well, not everybody's American, but you get it. It's the American people spending this money on different things. Okay, that gives you a better idea of what those numbers mean. We're going to do the same thing with our other numbers because these numbers are also very, very large, and I'll illustrate that to you. Okay, and let's start with the first number, which is the 343 meters per second. Now, you have used maybe you have maybe used a shortcut before to deal with the speed of sound, and you might not have actually been aware of it. But if you're not aware of it, I'm going to make you aware of it. Because knowing a little bit about the speed of sound is really helpful in staying alive. Not the song, but in terms of how to deal with a lightning storm. Okay, so I'm going to erase this after taking a quick picture because I don't want to bend to the bottom here and take... it's going to be a little bit hard. So I'm just going to take a picture and then erase. I'll just post these later. Good. So maybe I shouldn't. I don't know. I'm going to erase this here. Okay. All right. All right. Good. Okay. So we're going to look at that number and we're going to say, okay, well, this is about equal to 333.3 meters per second, which is about 1/3 a kilometer per second. Okay, that's a good rule of thumb to remember the speed of sound by. If you're hardcore American, you can say it's 1/5 of a mile. That's pretty close as well. Okay, so taking this number, you might have done this before when you're out playing soccer or throwing the frisbee at the park, and suddenly the weather pulls up and you hear lightning. Oh, sorry, you see lightning. You see lightning. You hear the thunder. But it's the same thing, right? I mean, you're hearing the thunder, which is the sound the lightning makes. Okay, so you see the lightning, and then you might count until you hear the thunder. So 1 Mississippi, 2 Mississippi, 3 Mississippi. Okay, so if you counted to 3 Mississippi until you heard the thunder, how far away did the lightning strike? And some of you have already done this before. You know this. Some of you might not know this. I'm not sure. So you've counted to 3 Mississippi after seeing the lightning, and then you heard the thunder. How far away is the lightning strike? How far away has the lightning strike happened? Answer on the chat. Cool. Okay, so 3 seconds each second. Good, nice, good, excellent. Hi, Errol. Good, 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 excellent. Good job, team. Good, excellent. So, and of course, the implication, and this might not be clear, is that when we see the lightning, we see the lightning instantaneously. Okay, so on human scales is okay, and that generally is true for sound as well, because when I talk to you in the classroom, it's not like Hello, what happens now? Like, although that might happen in the video, so that's confusing now. But anyway, the point is, when you see somebody speaking, you normally see their mouth talking and the sound coming to your ear pretty much instantaneously, because the speed of sound for short distances is also basically instantaneous. Over a few meters, it just takes maybe 1/100th of a second to get to you. So you can't tell the difference in terms of your speaking not being matched up, your mouth moving to the sound you're hearing. But in this case, it's big enough that it does matter, okay, over these kind of distances for sound, because it takes several seconds to get to you. Okay, good. Now, however, light is not infinitely fast. Okay, so light is not infinitely fast. So for example, we're on Earth. There we are, and here's the moon. Okay, and the moon is 384,000 kilometers away. That's a big distance, okay? And this is so big, you can't really picture what that means, right? Because it's kind of like those $2.2 trillion. You're like, wow, that's really far. But on the other hand, if I told you the sun and the earth were 150 million kilometers apart, your response would be, wow, that's really far. But really, you don't have a good way of getting a grasp of how big they are, because these numbers are not on a human scale. You're never going to, well, in your entire lifetime, you might walk this far, but the furthest you might run is maybe, yo, hi, Sadie. Carlos and James, those are the only two I think I'm missing. Otherwise, everybody's here. So really, really long. We can't picture that until we put it in a scale that makes sense. So we're going to take these numbers and we're going to think about them by thinking about how long the light took to get to us. So the moon, we see the moon at night. Sometimes it's not there. Where is it? Oh, other side of the earth. Okay. Anyway, so the moon we see, and the light travels, of course, at this speed, 300,000 kilometers per second, and is traveling 384,000 kilometers. So the time it takes for the light to get here from the moon is equal to the distance that it's away divided by the speed of light. And this is, of course, c in this case, okay? All right, so you guys work that out. How long does the light take to get to us? And type that into the chat. Go. Whoa. That is too big. Okay, that's fine. Okay. I get 1.3 seconds for the time. So it takes 1.3 seconds for light to come to us from the moon. And 1.3 seconds, we have a pretty good idea what that means. 1 Mississippi, 1. That's how long it takes for the light to get to us from the moon, which is not instantaneous. It's also not really long, but it's kind of like the time it takes for thunder to get to you for a lightning strike that's so close, you better be getting shelter very, very fast, okay? Because it's very close to you. Now, what we're going to do, yeah, good, thank you. So what we're going to do is we're going to take this distance, which is incomprehensible to you or me or anybody because it's so far. And we're going to say, we're going to call this distance 1.3 light seconds. So instead of talking about distances on these scales, yep, 1.28 is right. Yep, good. So 1.3 light seconds is the distance to the moon, or you can just round it to 1 light second. That's okay. If you just want to remember that, that's a cool fact to have in your head. Light from the moon, it takes about 1 second to get to us. Okay, so 1.3 light seconds is the distance to the moon. We can do the same thing with the distance to the sun. Let's do that over here. So the time for the light from the sun to get to us is 150 million kilometers. So this would be 150 million divided by 300,000. Okay, and that's going to be, this is in kilometers. This is in kilometers per second. Good. Is it focused enough? I think it is. Good. So let's figure that out. So we got the distance, the time to the sun, and we can find the time it takes light to get to us from the sun. And that's 500 seconds. Okay, so that's again informative, however, not super informative because nobody talks that way. 500 seconds is correct, Saskia. Good job. So 500 seconds is the time it takes light to get to us from the sun. So the light you're receiving right now, maybe through your window, I'm looking out the window, there's not sunshine, but the light that comes diffused through the clouds is from that sun. So it's taking 500 seconds to get here. But nobody talks that way. Hi, Carlos. But nobody talks that way. So if I said, boy, I'm an old man, but I can still run a mile in 500 seconds, you'd be like, weirdo, nobody talks like that. Nobody says they run a mile in 500 seconds. They would say, like Yuli is saying here, you run a mile in 8 minutes. Okay, so we take that and we say, this is about equal to 8 minutes. So that means we can take this distance we have right here, which is 150 million kilometers, and we can say, we call that distance 8 light minutes. 8 light minutes. Okay, so that's a good way of expressing that. Now we have a much better idea of how to talk about these numbers than we did previously, because we can talk about the distance to the moon, the distance to the sun, and the distance to the planets beyond the sun, and the distance to other stars now more coherently and have a better understanding of what that means. For example, we said the distance to the sun is distance to the moon is 1.3 light seconds. Now, 1.3 light seconds, that number right here is, okay, that's a number, right? And if you remember from the Apollo missions, flew to the moon. And in Apollo 13, they actually mention how long it takes to get to the moon with an Apollo capsule. Okay, they get the Saturn V rocket, they blast off Earth, and then they travel to the moon with this Apollo capsule. And how long does it take? You guys remember Apollo 13? They mention it. Maybe you just know. Does anybody know how long it takes to get to the moon, or took to get to the moon when humans were still able to do it, because we can't do it anymore? Any ideas? All right, well, couple of days. Good. It was 3 days. Okay, 3 days, what they said. 3 days there, 3 days back, 3 days. It took 3 days. So now let me ask you this question. Okay. Now, you shouldn't take a trip to the sun. That's stupid because the sun is really, really hot. Okay. But the sun is a pretty good proxy for traveling to another planet because the distance to the sun is comparable to the distance to the inner planets. Okay. Mercury, Venus, Earth, and Mars are the four inner planets of our solar system. And depending on where we're located at different times, we're the closest we get is like a third of the distance to the sun, I think, is the closest we get to Venus, and a half the distance to the sun is the closest we get to Mars. You get the idea. So when we want to consider traveling to other planets, like Mars is often sometimes something we mention, is we need to consider traveling about half the distance. I'll answer that question in a second. So we can't travel. If we want to go to one of the other planets, we'd have to go several light minutes, maybe 4 light minutes to be half the distance to the sun to get to Mars, for example. Whoa. Now think about just the time involved. If we assume that our spaceship that goes to Mars is just as good as our spaceship that went to the moon, okay, then we would have to think with a comparable speed that our trip to that planet, Mars, would take that much longer. Okay, so if we're looking at 4 light minutes compared to 1.2 or 1.3 light seconds, we're looking at a distance of approximately 200 times further. Okay, 200 times further. And that would mean that your estimate for a trip to Mars or another planet would be how many days? Okay, 6 months is optimistic. I think that's probably something you saw in one of the sci-fi movies, but yeah, something like that, because based on the 3 days to the moon, we'd have to be looking probably even at a year or year and a half, 2 years. Yeah. Now, here's the deal. So many things can go wrong. If you saw Apollo 13, great movie, by the way, great movie. If you haven't seen it, you should see it. Apollo 13, fantastic movie. And you can learn a lot about how about space travel, how it works, but also about the problems that arise and how difficult it can be. They succeeded, but they barely succeeded keeping those guys alive. It's a very dangerous thing. And to keep people alive for 2 years to get to, or 1 year, or even 6 months to travel in space and then do something there and then come back healthy and land them back on Earth, which people like coming back alive. That's good because you got maybe plans, for your life. Then it's very difficult, very, very, very difficult to do that. Okay, just something to keep in mind. So, trip to planet, months slash years. Okay, and of course, and this is now really scary, if we think about traveling to another star, I don't mean our star, the sun, but another star, which is light years away, light years away. And a year is 31 million seconds, 31 million seconds. So these other stars are maybe Proxima Centauri, I think, is 4 light years away or 3 or something like that. Let's say 3, just making math easy. It's 100 million times further away than our moon. So that means we'd have to spend 300 million days to get there at the same speed. That's not going to work. There's just no way with our current technology. Coming back to that question, Konstantin asked, why can't we go to the moon? We can't go to the moon because we kind of didn't maintain the technology. The Saturn V rocket was built specifically for the purpose of pushing us all the way to the moon. Currently, we are only able to put humans in orbit of the Earth. The International Space Station, the space shuttle that doesn't work anymore either, those are only a few hundred kilometers away. A few hundred kilometers above us is how far they are. So let's say 500 kilometers. So getting somebody 500 kilometers away from the Earth in orbit is one thing, but getting somebody 380,000 kilometers away to the moon and safely bringing them back is a completely different ballgame. Okay, so your flight to your space station takes just a few minutes, I think, 30 minutes, 45 minutes. I'm not sure exactly to get you docked or get up there. Now, again, that scale, 30 minutes to a space station compared to 3 days to the moon with all those different stages and boosters and rockets and all those things, a lot more complicated. And currently, we cannot do it safely. So we'd have to focus a lot of effort on getting it done. We could get it done, but we can't do it right now. Okay, that brings me to the end of the 30 minutes. I hope that was informative and or helps you understand distances and large numbers because those are important things. We will meet again tomorrow, okay? And we'll talk about waves more tomorrow. And this is the last week before spring break. I hope you guys are well. You are learning stuff this week anyway, keeping in mind to get better, get smarter, and all that stuff. And I'll see you around.